Write the Hindu Arabic number 145 in the Babylonian numeration system. Babylonian is a base 60 number system, so 145 is two groups of 60 plus 25, which in Babylonian is represented like this. Write the Roman numeral as a Hindu Arabic number. The three C's stand for 300. The XL is 40, and the VII is 7, which means the number represents 347. Write the Mayan number as a Hindu Arabic number. Mayan is a base 20 system, although this place represents 360s. So there's one 360, there's 9 groups of 20, and there's 11 groups of 1, which is a total of 551. Write the following as a base 10 number. So remember, in base 10 we're looking at powers of 10 representing the places. So in this case we have 6 groups of 10 to the 4th, 8 groups of 10 to the 1st, and 3 groups of 10 to the 0, which means we have the number 60,083. Write 220 base 5 as a base 10 number. In base 5, the first 2 is in the 25's place, the second 2 is in the 5's place, and the 0 is in the 1's place, which means we have 60 in base 10. Write 159 base 10 as a base 12 number. We have to think of 159 as one group of 144, one group of 12, and 3 ones. So in base 12, this number is 113. Find the sum. The sum of these two numbers is 320 base 5. Find this sum. The sum is 1011 base 4. Find the difference. The difference is 365 base 8. Find this difference. The difference is 202 base 5. Find the product. The product is 350 base 12. Find this product. The product is 3818 base 9. Find the quotient. The quotient is 13 base 4. Find this quotient. The quotient is 41 base 5. How many divisors does 720 have? If we factor 720 into a product of prime factors, we can find the total number of divisors by looking at the numbers that we get by adding 1 to each of those powers and multiplying those numbers together. And we'll see that 720 has 30 divisors. What property of whole numbers is illustrated by the following? These are the properties you have to choose from. This is an example of the distributive property. What property of whole numbers is illustrated by this? This is an example of the commutative property of multiplication. What property of whole numbers is illustrated here? This is an example of the identity property of multiplication. What property is illustrated here? This is an example of the associative property of addition. What property is illustrated here? This is an example of the zero multiplication property. And what property is illustrated here? This is an example of the associative property of multiplication. What property is illustrated here? This is an example of the commutative property of addition. What number sentence is illustrated by this model? The model shows 1, 3, base 4, plus 3, 0, base 4 is equal to 1, 0, 3, base 4. What number sentence is illustrated by this model? This model shows 1, 2, 1, base 3 being divided into two equal groups. So it would be 1, 2, 1, base 3 divided by 2 equals 2, 2, base 3. The 2, 2 is the number in each of the equal groups. Use scratch addition to find the sum. So when we add, we can say 2 plus 7 is 9, and 9 plus 6 is 15. We show the 15 as a scratch and a 5. Now since we have no more 1's to add, we'll write down the 1, and then the regrouped 10 will be shown in the tens column. 1 plus 6 is 7, 7 plus 2 is 9, and 9 plus 8 is 17. The 1 in 17 represents 10, so we'll show that with a scratch. And the 7 is ungrouped, so we'll write that down. And then since we have a 1 scratch, that represents one group of 100 that we then place in the hundreds column. 1 plus 4 is 5. 5 plus 6 is 11. And then 1 plus 8 is 9. And the 1 scratch in the hundreds column represents a group of 10 hundreds, or 1,000. So our sum is 1,975. Use lattice multiplication to find the product, 716 times 53. So we'll start by placing the digits of the two numbers around the top and the right part of the rectangle. And then we'll draw our lattice and find the products of the individual digits. If we add in each of the diagonals, we're adding digits that have the same place value. And the number that we read around the left and bottom represents the product, which is 37,948. Use divisibility rules to determine if 99,450 is divisible by 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So let's start with 2. The number is divisible by 2 because it's an even number. For 3, we can say that the number is divisible by 3 because the sum of its digits is 27, and 27 is divisible by 3. For 4, we look at the number formed by the last two digits, which is 50. And since 50 is not divisible by 4, neither is our original number. For 5, we look at the last digit. And since the last digit is either a 0 or a 5, in this case it's a 0, the original number can also be divided by 5. For 6, we look back at what happened when we look to see if the number could be divided by 2 and 3. And in this case, the number could be divided by both 2 and 3, so it's also divisible by 6. For 7, we'll try the cross-off double subtract method. So if we cross off 0, double 0, and subtract that number from 9,945, we have 9,945. We'll cross off the 5, double the 5, and subtract that from 994, and we get 984. We'll keep doing this until we've got a number that's small enough that we can see whether or not it's divisible by 7. So cross off the 4, double 4, we get 8. Subtract that from 98, we get 90. 90 is small enough for me to see that 7 will not divide into 90 without a remainder. So we can say no, this number is not divisible by 7 because 90 is not divisible by 7. For 8, we look at the number formed by the last three digits, which is 450. And since we can't divide 450 by 8, we can't divide our original number by 8 either. For 9, we look at the number that we get when we sum all the digits, which is 27. And we can divide 27 by 9, so we can divide the original number by 9 as well. For 10, we look at the last digit of the number. And since the last digit is a 0, we can divide it by 10. And for 11, we'll look at the numbers that we get when we add alternate digits. So 9 plus 4 plus 0 is 13, and 9 plus 5 is 14. If we subtract those numbers, we get 1. And since 1 is not divisible by 11, our original number is not divisible by 11 either. In the following number, one digit has been replaced with a blank. Find all possible digits that could be placed in the blank to make the statement true. The rule for divisibility by 3 is that the sum of the digits must be divisible by 3. So if we sum the digits that we have so far, we get 17. That means the remaining digit would have to give us something that would be divisible by 3. And if the remaining digit is a 1, 17 plus 1 is 18, which is divisible by 3. So that would be a good digit to use. 4 would also work because that would give us a sum of digits of 21. And 7 would work as well because the sum of the digits would be 24. And all three of those sums are divisible by 3. So the three possible digits we could have to replace the blank are 1, 4, and 7. In this number, we've replaced one of the digits with a blank, and we want this number to be divisible by 4. So what could the digits be that go in the blank? Well, the rule for 4 is that the number formed by the last two digits has to be divisible by 4. So the first digit that could possibly be in that blank is a 1, because 16 is divisible by 4. A 3 in the blank would work as well, because that would give us a number formed by the last two digits of 36, which is divisible by 4. 56 is also divisible by 4. 76 is, and 96 is. So the possible numbers that we could put in the blank are 1, 3, 5, 7, and 9. Use the prime factorization method to find the least common multiple of 18 and 90. We can factor 18 as 2 times 3 times 3, and you might need to make a factor tree to find that prime factorization. 90 is 2 times 3 times 3 times 5. To find the least common multiple, we need to find the pairs of factors that these two numbers have in common, and we also need to find all the factors that they don't have in common. So they have a 2 and a 3 in common, and then they also have a 3, 3, and 5 that they do not have in common. So if we multiply those factors together, the 2 and 3 that they have in common, and the 3, 3, and 5 that they don't have in common, we find a least common multiple of 270. Use the prime factorization method to find the greatest common factor of 18 and 90. So we'll find the prime factorization of the two numbers. Once again, you might want to use a factor tree to find that prime factorization. And then we'll find all the factors that the two numbers have in common, which in this case are the 2 and the 3. Multiplying those two factors that they have in common together gives us the greatest common factor, which is 6. Use the intersection of sets method to find the greatest common factor of 18 and 45. So we need to write down two sets of numbers, which are the factors of each of these numbers. So the factors of 18 are 1, 2, 3, 6, 9, and 18. And the factors of 45 are 1, 3, 5, 9, 15, and 45. We need the common factors of those two sets, which are 1 and 3. And then we need the largest of those common factors, which in this case is 3. So the greatest common factor is 3. Use the intersection of sets method to find the least common multiple of 18 and 45. So we need two sets of numbers. One is the multiples of 18, and the other is the multiples of 45. The common multiples of those two sets start with 90 and then continue on with all of the multiples of 90. But the least common multiple would be the smallest of those common multiples, which in this case is 90. Use the Euclidean algorithm to find the greatest common factor of 252 and 408. So we start by dividing the larger number by the smaller number, and since we don't have a remainder of 0, we'll take the divisor 252 and divide it by the remainder 156. We still don't have a 0 remainder, so we'll take the divisor 156 and divide it by the remainder of 96. We still don't have a 0 remainder, so we'll take the divisor of 96 and divide it by the remainder of 60. We still don't have a 0 remainder, so we take the divisor of 60 and divide it by the remainder of 36. Since we still don't have a remainder of 0, we'll take the divisor of 36 and divide it by the remainder of 24. The remainder is still not 0, so we take the divisor of 24 and divide it by the remainder of 12. And we finally have a remainder of 0. That means that the last divisor we had, which was the 12, the divisor that finally gave us the remainder of 0, is the greatest common factor of 252 and 408. Organize the prime factorizations of 28 and 36 in the Venn diagram. So we'll find the prime factorizations of the two numbers. You might want to make a tree diagram to find the prime factorizations. We can see that there are two factors of 2 that 28 and 36 have in common. So those two factors of 2 would be in the intersection of our two circles. 28 also has a factor of 7 that 36 doesn't. And 36 has two factors of 3 that 28 does not have. So now let's think about our operations of intersection and union, and how we could use those along with these two sets, set A and set B, to describe what's going on. The least common multiple of these two numbers is A union B, and the greatest common divisor of the two numbers is A intersect B. So in this case, the least common multiple, A union B, would consist of all of the factors that we see inside both circles. And if we multiply those factors together, we get 252. And the greatest common divisor is the intersection of A and B, which in this case is the two factors 2 and 2 multiplied together, which is 4.